We begin with the P-type substrate, a silicon wafer that acts as the foundation for CMOS transistors. This wafer is carefully prepared to ensure a pristine surface for all the steps that follow. The wafer is placed into a furnace at 1000 degrees Celsius. A precise flow of oxygen causes a chemical miracle. A thin, glass-like oxidation layer grows over the surface. This layer is not decoration. It will mask, protect, and direct what comes next. Now, a light-sensitive photoresist is spun onto the wafer as smoothly as paint on glass. This isn't art. This is the first step of photolithography, where light will carve paths into silicon like sunlight through stained glass. A mask is placed over the wafer, like a stencil of the future circuit. UV light is fired. It shines through transparent regions of the mask, chemically altering the photoresist beneath. Some regions harden, others stay soft. The wafer has been kissed by light and encoded with the pattern. The wafer is bathed in a developer chemical. The unexposed photoresist dissolves, revealing windows in the oxide layer beneath, entry points for transformation. Where the SiO2 is exposed, it is now etched away using hydrofluoric acid. This reveals the bare silicon, allowing future dopants to enter only where they're truly needed.
The photoresist is now stripped off. Its job is done. What remains is a wafer with etched oxide patterns, regions open, regions protected, a layout that will guide the rest of fabrication.
In select regions of the P-type wafer, phosphorus or arsenic is diffused in, creating N-wells, homes for PMOS transistors. This step is controlled with precision. Depth, concentration, uniformity all define the final transistor behavior. The temporary oxide is removed again to prepare for the most important structure, the transistor gate. A thin gate oxide is grown, the ultimate insulator. Over this, polysilicon is deposited, durable and conductive. This will form the gate electrode, controlling current between source and drain. It must align perfectly, and it will, thanks to the self-aligned gate process.
Using photolithography again, the polysilicon is etched, leaving only what's needed. The gate is now carved, the control terminal of every transistor, positioned with submicron accuracy. Another oxide layer is grown to protect and isolate the wafer during the next doping operations. Windows are opened in the oxide over the NMOS regions. N+ dopants flood in, forming source, drain, contact. These regions are now ready to conduct, controlled by the gate above. Once again, oxide is stripped, making way for the PMOS regions to be activated. Now P+ impurities are introduced in the N-wells. They form the source, drain, and contact for PMOS transistors, completing the CMOS pair.
To ensure no electrical noise spreads, thick oxide barriers are grown in inactive areas. They're the fences between neighborhoods, ensuring safe communication inside the chip. An ultra-thin layer of aluminum is deposited across the wafer, covering everything like a mirror. Using photolithography and etching again, excess metal is stripped away, forming physical terminals, where voltage will enter and signals will leave. Finally, each terminal is labeled source, drain, gate, for both NMOS and PMOS. And there you have it, the CMOS fabrication process. Thanks for joining us on this journey through semiconductor fabrication. Stay curious.